Hello, everyone. We're now going to talk about bootstrapping. Now, I'm a political junkie. I'm a political junkie. I care a great deal about politics, and I follow political polls. And if you follow political polls, you often know that those polls comes with what's known as a margin of error. And you might see this at the bottom of the screen, right below the poll. They'll say margin of error of plus or minus 3 percentage points, something like that. It's the margin of error quantifies the uncertainty that we attach, the amount of uncertainty that comes with a statistic. Because all statistics, when computed from random data, are uncertain. If we believe that the data is not representative of the entire population, but instead is a subset of that population, and a subset chosen randomly with equal likelihood in some sense of getting every member of that population, then you should then that means that you get an estimate of the parameter of interest. That estimate is random itself, and where exactly the actual parameter that you're interested in is not necessarily known. And in fact, it's quite likely that your estimate is not equal to the true parameter value, and what you want to do is estimate the uncertainty that's associated with your parameter, and based off of your parameter, where you think the true parameter probably is. And you can't really say where exactly it is, because if you did, then this entire issue would be moot. But you could give a range instead, describing where you believe it is, where you say, okay, we think that the actual proportion of individuals supporting candidate X, that number is going to be within plus or minus 3 percentage points of the number that we're reporting. Something like that. That's the idea of a confidence interval. The confidence interval comes from basically adding or subtracting our margin of error from our statistic, and we believe that the true parameter value is going to be in between the lower and upper bound of that interval. And there's a chance that we're going to be wrong. There's a chance that the margin of error is going to be above or below this interval. And we reported some uncertainty, but we missed it. But we could potentially quantify how certain we are that the true parameter value is in the interval that we're reporting. Or adopt a procedure. This is actually what we're going to do. We're going to adopt a procedure that has some probability of capturing the true parameter value. As in, the procedure itself has some probability of actually capturing the true parameter. Whether the interval itself has the parameter of interest, we don't know, and we may never know. But we know that the procedure has a certain probability of capturing the parameter value, and if that probability is high enough, which it's never 100%. Like, there's no such thing as a 100% confidence interval, because such a confidence interval is trivial. It would basically be negative infinity to infinity, or 0 to 1 if we're talking about a proportion, or maybe 0 to infinity if we know the parameter value is not going to be negative, but such intervals are not of any interest. It's going to be something like 95%, where the probability that this procedure actually captures the true parameter value in these circumstances is 95%. So, and based off of the high probability that this procedure has to capture the true parameter value, we believe, we find basically believing that this interval contains the true value reasonable. All right. So later in the lecture part of this class, we'll talk about how to compute confidence intervals, what I've described as a confidence interval. We're going to talk about how to compute those exactly under specific circumstances using mathematics and probability theory. Here we're going to see a popular computational method known as bootstrapping. The idea of bootstrapping is that we are going to estimate the sampling distribution of a statistic of interest. This is the distribution that the statistic drawn from this population has. Its probability distribution as opposed to the population's distribution. So we're going to estimate that distribution. That distribution is going to depend on the true parameter value. In the case of, say, the mean, the sampling distribution of the sample mean is going to contain the population mean, since the expected value of the sample mean is the population mean. So we use that distribution and look at quantiles of that distribution to try and capture our true parameter value. Okay, so we need to estimate that distribution. We do so using the bootstrapping procedure. What the bootstrapping procedure does is it views your sample as if it were the population. And whenever you get a sample, what you obtain is an empirical distribution. An empirical distribution is the distribution that results when every observation in your sample is equally likely to be drawn, where you treat your sample as your sample space, or as the possible values that you could see. You treat it as if it's the entire population, and then choose every member, and then you choose a member of that sample, with every member of the sample having equal likelihood to be chosen. So if you have a sample size n, the probability of picking any number from that sample is 1 over n. You imagine you take your sample's a bunch of numbers, you put them into a hat, and then you draw a number from the hat, which is one of the individuals in the sample. And that will be the empirical distribution that we saw for the population. So we sample randomly from the empirical distribution and recompute our statistic many, many times. And when we do this, we so basically all right, going back a little bit, we are generating fictitious samples from the population by treating our sample as if it was the population. We sample from our sample with replacement. So, and that's a critical part, because if we sample without replacement, we would just get the exact same sample over and over again. So you have to do it with replacement. And you then recompute your statistic whenever you're generating fictitious samples this way. You do this many, many, many times, and the resulting distribution of your statistic will be the estimate of the statistic's sampling distribution, and then you can use that sampling distribution to come up with an interval that supposedly will contain the true population parameter. You could look, for example, at the 2.5th and 97.5th percentiles, and that will get you a 95% confidence interval for the true parameter value. Okay, so let's see how we could do this. We have a vector x. This vector contains the data set under investigation, so it contains if we're, say, studying people's weight, for example. I like to talk about weight because it's easy to think about. So let's say that we're interested in people's weight. Okay, we're going to we have a sample of individuals' weights in some study, and we want to know what the mean weight is. We could compute the mean of the individuals, the mean weight of the individuals in our sample, and that would be fine. And we would get an estimate then for the mean weight of individuals if we sampled appropriately. And that's fine. There's nothing wrong with that. It's just that we know that that's not going to be the mean weight of all individuals in the population. So we're going to come up with an interval that we believe will probably contain the true population of the mean. The true mean of the population. Other way around. So we then randomly pick individuals from our sample with replacement to do fictitious studies. You know, if we were to do this study again and again and again, we get fictitious samples. And then we compute the mean for each of those fictitious samples. We do this many, many times. We end up with a distribution of the sample mean using all of those means that we got before. And we then study that distribution. And we might say, Okay, we believe that the true mean of the population is going to be between the 2.5th percentile of the simulated distribution, simulated by recomputing these means from fictitious samples, and the 97.5th percentiles. And that will be a confidence interval. So here is our so to do the random sampling, we would use the function sample. We use sample. Here is our observed sample of weights, x. We're going to make it so that our fictitious samples have the same length as our original sample, which means, in all likelihood, that individuals in the sample will be repeated, which is fine. We actually want that, and we say replacement equals true, so we should have sampling with replacement. That's how we're allowing to repick individuals, because this is simulating the sampling with equal likelihood that we assume our data came from. All right, and then we can use the quantile function to get a confidence interval by looking up, like for example, the 2.5th and 97.5th percentiles of the sample of simulated means, because this procedure generates one fictitious sample, and we would compute the mean of that fictitious sample. All right, but we're going to need to do this many times. All right, let's see an example now. We're going to use the chem data set from the mass library. This is the amount of copper in flour and parts per million of some data set. So loading that library, here's the data set of interest. Here's the mean of that data set. So we believe that the amount of flour and parts per million, the amount of copper in flour and parts per million is about 4.28 parts per million parts. Okay. We could generate a fictitious sample like so. Here is the fictitious sample. There's likely some duplicates in the sample. That is not a surprise. In fact, like here, for example, is a duplicate. I don't think 3.10. Well, 3.7 appeared a few times in the original, but I don't think that 3.10 did. So that is a known duplicate right there. But that is a feature, not a bug. Okay? So we would then compute the mean of our fictitious sample to get a simulated mean. Okay? And this will be one mean from our estimated sampling distribution. Okay. We did that once. We now need to do that a lot of times. By a lot, I mean 2,000. Why 2,000? It doesn't have to be 2,000. It could be 3,000. Just make it big. All right? So 2,000 times we are going to repeat this procedure, where we compute the mean of a fictitious sample, where that fictitious sample is generated by sampling with replacement from our original sample. We're going to do that 2,000 times to get a sense of excuse me, to get a sense of what the distribution of the sample mean is. And in fact, we could look at that distribution if we wanted to. We could do so with maybe a histogram. All right, so that's what the histogram looks like. Rather discrete. We could maybe use a density plot. So plot density mean boot. Interesting. Well, that's curious, but yeah, I guess that's the sampling distribution. And then we could look at the quantiles of our sampling distribution to come up with a 95% confidence interval. So in this case, we wanted a 95% confidence interval. So our lower percentile will be 2.5, and our upper percentile will be 97.5, or 0.025 and 0.975. And this is the resulting interval. So basically, we believe that the true amount of copper in flour and parts per million, the true mean, is going to be in between these two numbers. All right. If we wanted to, we could get a 90% confidence interval by changing 97.5 to 95 and 2.5 to 5. That gets us a 90% confidence interval, which is narrower, but also less likely to actually have the true mean in it. in some sense. But what exactly I mean by that, I'm going to reserve for the more mathematical treatment of confidence intervals. All right, so that concludes this video. Hopefully it was enlightening to you. This is known as the bootstrapping procedure. It's extremely popular. It's popular because, yeah, you can do the mathematics and get precise intervals in certain contexts, but the bootstrapping procedure is extremely robust. It's extremely robust to assumptions. It has very few assumptions, basically. The mathematical procedures have strong assumptions. Like, it might assume that your data came from a normal distribution. Bootstrapping doesn't care. Or at the very least that your sample size be large. Bootstrapping doesn't really care. So that's one thing that's nice about bootstrapping. That's one reason why it's often used, because it's very likely to work. Yeah, so always be aware of it, because it does get used. It's very popular. But all right, that concludes this video, and also technically lecture 6. So I will see you later.